Okay, so let's continue our discussion about the RISC-V instruction set architecture. And we kind of ended our previous lecture on the encoding and various instructions and registers that the RISC-V RV32 CPU, RV32I CPU provides us with. What we are now going to take a look at is what are the tools that we are going to use to convert the assembly or convert the text. Could be C code, could be assembly code. What are the tools we'll use to go from text to RISC-V assembly, RISC-V machine code? Okay, so I have the instructions provided here. If you have a Linux machine, you could essentially kind of, try this out locally. But what we are going to do is we are going to go to the machine that we had created as part of earlier videos, which is the code spaces. Right? And so I'll wait for the code space to launch. So the code space is launched. It's getting ready. We'll just wait for it. And the interesting thing is that I have updated the README. So in case you have a machine that you created earlier, by watching the earlier videos, what you need to do is ensure that, when you do git status, it says that your working tree is clean. And if it says your working tree is clean, right? So just type git pull minus minus rebase, and what it will do is pull the latest changes, and then when you check the readme file, you will have the commands handy here. Again, if you see that you have, let's say, from the um, previous videos, if you have something like bmp.h, which was the case. So when you do git status, you will see something like so. There are untracked files. So what you can do in that case is type git reset minus minus hard. And when you do this, what happens is all the files are deleted that you have not committed using git. Complicated details if you haven't used git before. But the idea is that we have to discard the earlier changes. And if you see, okay, the file did not go away. So we are going to use git clean minus ftx. So when we do that, it says, hey, I'm removing the file that I was not tracking, and bmp.h is gone. So any files that we added as part of previous experiments, those will be gone. And then when you do git status, it should say that the working tree is clean, right? So the idea is that we reset git or repository to a clean state and then pull the latest changes, and those latest changes is where the readme file is updated. Again, this is midway of the course, so chances are that by the end of the course I have modified this heavily. But the key is look for these commands here, and what I want you to do is go ahead and kind of one by one, or let me just actually type those. So I'm going to full screen this, right, and then increase the font size here. Okay, move this on this side, and then type first sudo update -y. So what this command does is it updates the package list that the Linux machine has, right? And then the second command here installs few utilities, right? And we'll take a look at what those utilities are. Okay, it has to be sudo apt update -y. -y is for, okay, don't ask me for any permissions, just go ahead and proceed with the operation. So what it's doing is it's kind of updating itself, the package list. And the second one, what we are going to do, and this is interesting now because this is what we wanted to originally discuss. And yeah, so here the GCC RISC-V 64 unknown ELF, this command or this package here contains the toolchain, and I'll show you. But toolchain is toolchain, right? So this package here, essentially when it gets downloaded, it downloads the programs that are part of the toolchain that, the industry folks or the experts or the professionals refer to as toolchain, and I'll show what is part of that. This will come to in a bit. Um, the GDB multi-arc here is the GDB debugger. It's a GNU debugger, and the multi-arch here essentially provides us the support for RISC-V. Right. So we have a utility, the GDB, the debugger, that can be connected to our programs, and then we can look inside the CPU and look at the state of our program. And that way we'll be learning the C language, much like a hacker. So hopefully, most of you who are watching want to become hackers. If not, never mind. All right, so GDB is for debugging purposes, for us to be able to look inside our program and see what's going on at the CPU and a system level. So that's for that. And the RISC-V GCC, the package here, will get us the toolchain. Let's talk about the QEMU system MISC in a bit. So we'll talk about this in a bit. Let me go ahead and issue this command first, execute this command first. So all you have to do is kind of copy this and then come down here and then paste it, right? And once you paste it, hit the return key. What will happen is it will go ahead and install. In my case, before recording the video, I had already attempted these commands. So in my case, it says, hey, everything's already installed, so no problem. Okay, cool. So now first, let's talk about what QEMU is. And for that, we are going to need a blackboard. Okay, so we talked about CPU, right? The Linux machine that we have is most likely running on ARM64 or x86 machine, x86, I think AMD 64 or something like that. AMD 64 or something like that. Now the problem here is we could have just as well compiled our C program for these architectures and directly run it on Linux, but that's not what I want to do. What I want to do is take you down to the bare CPU and run a C program from there without any of the operating system, right? And why do I want to do that? That is intentional. What this will force us to do is, as we learn the C language, we'll be able to correlate everything down to the CPU and the system, and the operating system will not get in between. So usually what happens is you have the hardware, then there is an operating system, and your program is running here. So most people learn the C language here. Oh God, my habit of not being able to spell correctly while I'm speaking. Hopefully I spelled it correctly. So most people learn C language by writing programs here, and then they cannot separate the C part from the OS part from the operating system won't let you touch the hardware directly. So there are a lot of complications, and the essence and the beauty of C goes missing. People cannot appreciate that or cannot even learn the insights. So for those reasons, I've decided to eliminate the need for an OS, and we will go straight down to the hardware. But now the challenge is you need to have an hardware, and I need to kind of also have that hardware. So to do away with that requirement, the open source community has done something amazing, which is they have created a software called QEMU, which is called Quick Emulator. What it can do is it can mimic the behavior of a CPU. It can act as if it is a CPU. And what does that mean? It means QEMU, if you give it a binary, it'll understand or decode your binary, understand the bit positions, and this software will then act like the CPU. And let this idea sink in. The whole point is it's a software that acts like a CPU, acts like a system with memory and CPU, right? So QEMU, you can think of it as a CPU, some memory, And there are other things, but we don't care about that. But it's a software that acts like a system. It mimics a system. And now the interesting part is what we're going to do is we're going to ask QEMU, instruct it, so to speak, to act like a RISC V 32i type of CPU, right? So what we'll then be able to do is spawn a software that acts like the CPU, load our programs into it, and then kind of put a hook through GDB into this machine, into QEMU. We can connect GDB to this, and then we can look at what the CPU is doing, how it's interacting with the memory, things of those nature we can learn. Now, one could argue, hey, can't we do this on hardware? Yes, it can be done. All of this can be done on the hardware. It's just that you will need to have that hardware, and I'll need to kind of do a lot of judo to show you the hardware. So I'm skipping that part. Maybe towards the end, it would be worthwhile to take our, one of our C programs and run it on a hardware. And I'll try to demo that towards the end of the course. Okay, so hopefully now you understand the role of QEMU. Right? And what we are now going to do is, so this is what has installed the QEMU for us, right? Remember, it's a software that acts like the RISC-V CPU connected to a memory. And that's what we need to be able to probe what's going on at this CPU level so that we appreciate what a C code does at a hardware level, what are the effects it has. Perfect. So now let me show you different parts of the toolchain. So what I'm going to do is simply type RISC-V and hit return, but nothing happens. So I'm going to type GCC and hit return and nothing happens. Well, something happens, but that's not what I intended. Okay, perfect. So when I type RISC-V 64 and hit the tab key, it kind of completes rest of the command. And if I hit the tab key again, what it is doing is it is listing the possible commands, right? And my claim now is all of these utilities that you see here, but each of them is a program. So all of these are part of the toolchain, right? Are part of what toolchain? The GCC toolchain. It's the compiler collection, GCC. So these are all part of that. And so what all do we have? So we have the assembler right here. Assembler converts assembly code into binary. Then we have got somewhere GCC. Okay, that's GCC right here. Then we have got the linker. Then we have got many GCC is here also. This is some specific version of it. This is the general GCC. Well, the difference between them is just version number and some internal details which I am unaware of. I tend to use just the GCC that does the job for me and done. Okay, so we have the assembler, we have the linker, we have the GCC. Then there are other supporting tools like, okay, reading an ELF file, executable and executable and linkable file, if I got that right. Then there is a utility to check the size. There is object copy, object dump. I don't know what an M is. I have used it, but I don't know the full form of it. Then there is address to line. So given a memory address, you can convert that instruction to the line of code in the C source code. Things of that nature can be done. So debugging related tools, this is the archiver, which can help us take multiple object files, and we'll talk about what object files are. Take multiple object files and stitch them together as a library. So if you have heard about the glibc, the standard library, and so on and so forth, well, they were created using AR command. All right, so these are like the different tools that come as part of the GCC installation command, right, which we had right here, right? And then we have the GDB multi-arch or multi-arc, and QEMU system MISC is for the QEMU. Oh, let me just show you that. QEMU. So the QEMU system MISC essentially installs QEMU for many different variants of processors, and we are interested in this one. All right, the RISC-V 32. We are interested in that. All right, so this was just a tour of an introduction and a tour of the toolchain, the QEMU, and then the GDB multi-arch. So let me also show you that real quick. And in the next lecture, what we'll do is we'll dive into writing the simplest assembly code first, assembling it down to kind of the binary, looking at the binary, the encoding, and then also executing it on QEMU. So once we are done with that, we kind of know the journey of, okay, here's the ISA, here's the assembly, here's how it got converted into machine code, and here's how the CPU consumed it. All right, so this was GDB multi-arch then. It kind of says it's GNU debugger, the GDB, so on and so forth. I'll just go ahead and do a queue. All right, so with this, hopefully you're convinced as to what our tools are, what the toolchain and the supporting utilities are. And in the next one, let's dive into writing an assembly program.